at Google Research, where Key has been working on machine learning for computer vision and NLP. Key was previously an AI resident at Google. His research interests mostly include multimodal learning, vision and language, vision and language research, and also generative models. Prior to joining Google, he has completed his undergraduate study at the Singapore University of Technology and Design in 2019. So I think JY has a lot of so interesting work recently on grounded visual generation, especially such as text-to-image synthesis based on the localized narratives, and the key also has been working on some other work related to embodied vision and language task. So let's welcome JY for the talk. Thank you.
Thank you so much. You can see my slides, right? I can't see it myself, so I...
Oh, I see. Yeah, so we can see your slides.
Okay.
And your voice is, yeah, good.
Okay, that's great. Hi, everyone. Thanks, Joe, for the introduction. So as mentioned, I'm JY, and I'm a research engineer at Google. And it's my pleasure to be here today for the Vision and Language Summer Talk Series. So my talk today will be on grounded visual generation, as you probably already know. And I'll be sharing some of my ideas in generative models and also 3 recent works in the domain of grounded visual generation. So I think everyone here has seen a lot of generative model results, especially recently. And I think we can all agree that these deep generative models are very incredible. So on the left, you can see Big GAN, which was published like 3 years ago by now, which has very convincing synthesis results on open images classes. So Big GAN is a class conditional GAN. You provide it with a class label of 1 of 1,000 ImageNet classes, and it's able to synthesize a realistic and plausible image just from that class label. So examples include being able to synthesize very realistic wolves, mushrooms, and you can see that Big GAN has also learned some properties of the real world. For example, this bubble has very realistic reflection, and in the fountain here, you can see that it actually is able to synthesize a reflection in the water. Other sets of models include the very impressive style GAN, which does unconditional generation from a random noise vector sampled from usually some normal distribution. So style GAN is able to synthesize very realistic faces, animal faces, and other examples. More recently, I think like what I call grounded generative models are even more impressive. So one example that I've been working on, and I think a lot of the community and people here have seen in recent weeks, is the text-to-image synthesis task. So the text-to-image synthesis task is if you provide a natural language description to a model. For example, a bus pulls over to the curb close to an intersection. The model should be able to synthesize a realistic image that is well aligned to the language description. So in this case, the model that we recently published, XMC GAN, is capable of synthesizing a realistic bus, a realistic road, and also you can see that it's quite well aligned with the description in this case. So there's a curb close to the intersection here. And I think these results on the right are a lot more impressive in that they come from the recently released CLIP and VQ-GAN models that probably everyone here has seen floating around on Twitter. So, for example, this caption, a castle made of jello or donuts surrounded by a moat made of ice cream or donuts. It's able to synthesize almost exactly this image. And what makes this more impressive than the XMC GAN style synthesis for realistic scenes is that these kind of images, they don't exist in the real world. And if there exist images of these in the training set generated by some artists, there's probably just one or very few examples. So somehow these text-to-image synthesis, these models have learned what are donuts, what are castles, and it has learned to composite donuts and castles and moats into a single image in a very coherent manner. And similarly, for the example on the right, which was released by this very active Twitter account today, it manages to generate a very nice looking image of dinosaurs in an infinity pool. And obviously, like this image doesn't exist in real life, but somehow this grounded generative model, VQ-GAN and CLIP, has learned how to represent it and synthesize a very appealing image. So I think these models are very interesting to me because they obviously learn useful knowledge about the world and they present it in very easily interpretable formats. In this case, it's just a realistic image. So It has learned to align realistic images with words in the caption, and it has learned to present this. And a practitioner or researcher can easily probe the model by changing certain words in the caption to see how the image changes. So these models are very interpretable. They are evidently very strong, and I think they are very interesting ways to look at datasets, large curated datasets. The inverse task of text-to-image synthesis, which is kind of image captioning, is also very interesting to study as a grounded generative model. So on the left, you can see that this image captioning model is conditioned on a class label. So if you provide a class label like ring, it synthesizes a particular caption. If you provide another class label like hen, it synthesizes a different caption. So by forcing it to be grounded to a certain description, you can force it to generate different things that are relevant for whatever task you want. And similarly, on the right, there's a style GAN paper from a few years ago, which similarly synthesizes captions according to different styles. So if you ask StyleNet to synthesize a romantic caption of the image on the left, it says something very different from if you ask it to synthesize a humorous caption. And I think these ways of probing generative models are very useful and interesting. So today I'll be sharing 3 recent efforts that kind of try to push the needle towards grounded visual generation. So the first is a work of ours titled User Attention Guided Text-to-Image Generation, where we try to attempt the task of generating images with both image descriptions as well as mouse traces, which are temporally aligned to the descriptions. And we claim that this is a proxy for user attention, and that may or may not be true, but it's an interesting task. We also attempt to improve text-to-image generation by imposing contrastive losses across language and vision modalities. So this more strongly grounds language modalities to vision modalities. And we show that this very simple idea of cross-modal contrastive learning actually improved the state of the art of COCO by about 60%. And lastly, I will also share a recent preprint on spatially grounded image generation. So this tackles synthesizing an entire 3-dimensional house from just a single input image. So the first work is titled Text-to-Image Generation, grounded by fine-grained user attention. The task is the following. So imagine that you tell a person to describe an image with words and with a mouse pointer. They might say something like, in the foreground of the image, there is snow and a railing, and in the railing, there is a person in blue skiing. So while they say there is a person in blue skiing, they would move their mouse cursor around the center of the image, and you would kind of be able to tell that this is where I want the person object to be synthesized, and I want this person to be dressed in blue. So given these descriptions, it's very intuitive for people to design images like this. And it's also very intuitive for artists to take such descriptions and mouse traces and synthesize a realistic image. So for example, given these inputs, this is an image that might be generated according to the inputs. So as Zhe mentioned just now, this work is done on the very impressive localized narratives dataset. And this was a recent dataset released by Google in 2020, which was presented at ECCV last year. So before I explain what the dataset is, I think I will play a short clip that will illustrate better.
In the front portion of the picture, we can see a dried grass area with the dried twigs. There is a woman standing wearing a light blue jeans and ash color long sleeve length t-shirt.
So this dataset was collected by getting annotators to describe images while simultaneously moving their mouse pointer across regions that they are describing. So as you can see on the left, this mouse cursor is aligned with whatever words were being spoken. And this allows us to curate a dataset of very densely aligned mouse trace and language descriptions. So the task that we formulate using the localized narratives dataset is what we call user attention grounded text-to-image synthesis. And in this case, we use mouse traces as a proxy for the attention of an artist or a user. Because of the way that localized narratives are captured, the average length is also much longer. So the average localized narratives description is around 41 words, which is around 4 times the length of the average MS COCO caption, which is around 10 words. So this also makes generation very hard, because not only does the generated image have to be aligned to this very long description, it also has to be spatially aligned to the mouse traces that the user provides. To solve this task or to attempt this task, we proposed the model titled Tracks.
JY, can I ask a question here?
Yes, go ahead.
So when you use this local narrative data set, do you just treat this these traces just as curves, or in fact you consider the the waiting the staying time for each dot on the curves? Because from the video I can see that when the annotator talk about something, in fact some the dots stay that place for several seconds and then quickly move to another dot. Seems that the dots that the cursor stops are really meaningful, and they're not connecting them together and not that meaningful.
Yeah.
So my question is that do you treat these traces as really lines or treat them as just separate dots?
Yeah, that's a very good observation. And I think we also observed that the speed of the cursor is actually a very useful indicator, because if you think about, like, in the context of image generation, if someone moves their cursor very fast across the picture, it means that whatever they highlighted during that fast movement is usually not very important. Whereas if they have more dense movement around a certain area, then that's the object that you care about. In this work, we didn't consider that temporal data, but I agree with you that it's a very useful signal.
Okay.
Yeah.
Okay, thanks.
Yeah, no problem. So for tracks, we actually treat it as a 4-stage problem. Given the image descriptions and mouse traces, we want to predict the object labels for each word in the description. So if my caption contains, in this case, there's a few words, person, skiing, trees in the description, I want to assign a class label to each of these words. And our class labels, actually, we just took it from MS Coco. So the, I can't remember, I think 180 or something classes from MS Coco, including the staff objects. We use those as object labels for the sequence labeling task. After retrieving the object labels, we use the object labels to retrieve semantic segmentation mask for each object. So for the person object, we retrieve the segmentation mask shown here. For the snow object, we retrieve this mask, and so on. Using these masks, we position them according to their mouse trace locations, such that we can get a complete scene mask of the entire image being described. And lastly, we pass this mask to a mask to image generation model to synthesize a realistic image at the end of it. So this 4-step approach, known as tracks, allows us to take mouse traces and image description and synthesize a realistic image.
JY, can I ask? So for the semantic mask retrieval module, are you really retrieve the individual mask from the mask bank from Coco dataset, or in fact you are generating masks?
Yeah, so in this case, we just retrieve the masks from MS Coco training set.
Okay. Okay, thanks. Yeah.
Yep. So the first step is sequence labeling with pixel semantics. As I mentioned before, for each word in the description, you want to assign it a class label. And the challenge in this lies in that you don't have one-to-one paired data. So for each description, you don't really have the class labels for each word in the description. And how we got around this was that we actually noisily annotate every description in localized narratives using the mouse traces and segmentation labels of the Coco image. So MS Coco contains very dense pixel level segmentation masks. And because we know which mouse traces correspond to each word in the description, we can retrieve the pixels that were highlighted and use that as the class label for the corresponding word by doing a majority vote. So in this case, when I say the word cat, we can see that the mouse traces corresponding to the word cat are these pixels highlighted here. And by retrieving the semantic segmentation class for these pixels and doing a majority vote, I can get the class label cat in that case. After retrieving this, we further refine it using very classical NLP techniques like the term frequency inverse document frequency model. And we also apply some alignment models to ensure consistency across the description and also across the entire training dataset.
Sorry, Jill, I do not understand the first step. So I think that there are two data sets here. One is the open image local narratives. One is Coco. On Coco, you have masks, but you do not have the the traces, the attention traces. On local narrative, it's the other way. But seems that now you are using both annotations, but there's no dataset that have both kind of annotations.
Right.
So this part I got confused.
Yeah.
Kind of what dataset you are training on, and how do you get both annotations?
I see. Yeah, actually, localized narratives contains annotations for both the entire MS COCO training set as well as open images. So in this case, like this particular method, we are only using the MS COCO stuff, which is why we have both localized narratives and the segmentation.
Okay, I got it. Okay.
Yeah, hope that's clear. We actually also test on open images, which I'll describe a bit later on. Yeah. So as I was saying, the tags are refined using these models, and we can see that this is actually very essential because if you just use the mouse tracers to assign class labels, it becomes very noisy. So the caption on the top with the class labels are assigned using just the mouse tracers. But if you apply this refining method, then the sequence labels become much cleaner. So in particular, you can see that the ski word is assigned the correct class after you perform this post-processing step. And lastly, we also fine-tune a BERT model over the HMM outputs, which we find that improves the sequence labeling results. So given these sequence labels, we next want to retrieve masks from a set of object masks in MS COCO. And these masks, we want them to be semantically aligned to the language description, but also spatially aligned to the mouse traces in the image. So how we do this is also kind of in two steps. The first is that we want to retrieve the top K images for a given caption. So this is done using a standard dual encoder model shown on the right, where descriptions go into one encoder, images go in a different encoder, and you compute the similarity scores. So given a description, we retrieve the top 5 images from MS COCO, and you can see that it generally allows us to retrieve images that are quite aligned to the language description. Given this set of 5 images, we then retrieve all the object masks from each image. So for example, this image, I might have 3 object masks, one of the dustbin, one of the refrigerator, and one of the floor, for example. We retrieve all these object masks, and for each mask, we compare it to the corresponding mouse traces describing the word. We take the mask that has the highest mean IOU with the mouse trace, which allows us to ensure that masks are spatially aligned to the mouse traces. So to recap, the previous step of retrieving masks ensures that masks are semantically aligned, meaning that if I'm talking about someone skiing, I retrieve person masks from people in skiing poses rather than of people in sitting poses or in driving poses. And the second step ensures that the masks, out of all the K masks that we retrieve, we pick the one that has the best alignment with the mouse traces. So we find that this achieves better performance than just using naive retrieval from just the mouse traces or just the language description. So lastly, now that we have our object mask, we can compose it into a complete scene. So we put staff masks, which are in the MS COCO definition. So these are objects that are usually more amorphous and large in area, like grass, water, or mountains. We put this in the background, and we layer things masks on top. So things are usually defined as stuff that are nouns or objects that are more smaller in size in general. So by composing it this way, we ensure that the stuff doesn't override the things, and we get a very dense and complete scene mask. And finally, the last step is that with this scene mask, we pass it through a pre-trained mask to image generator, which converts our mask object into a realistic image. And there are some drawbacks to this method in that the masks that we retrieve are kind of noisy because we are essentially like cutting masks from certain images and pasting them into with other masks that they weren't necessarily together at first. So this is not perfect, but we find that it's generally sufficient for our use case.
Hi, Joe. I have a question. So,
yep.
How did you determine the order of the masks? So, for example, the multiple foreground object.
Yeah, that's a good question. So, although I mentioned that like the stuff doesn't override the things, how we layer it is in the reverse chronological order. So things that are mentioned first go into the background, and things that are mentioned first go into the foreground, and things that are mentioned later in the description go into the background. So if I say something like there is a sea in front of a mountain, sea comes first, so it will appear in the front of the image. And this is backed by the intuition that things that are more important will generally be described first by the annotator. So annotators will generally talk about things that are more important before they move on to less important objects. So by layering it in this chronological order, you can ensure that the placement is somewhat correct.
Okay, I see. Yeah, thank you.
Yeah, thanks. Yeah, so I think that was the 4-stage model tracks, and now I'll present some qualitative and quantitative results. So on the left, you can see the localized narrative description. The first column is the original image. The center is the image generated from attention GAN, which was one of the state-of-the-art text-to-image generation models at that time. And on the right is the tracks generated images. So it's important to note that attention GAN doesn't have the mouse traces. So it's kind of like playing with one hand tied behind his back. But we observe that tracks images are generally much higher in quality, and they can generate very distinct objects compared to attention GAN, which usually generates just textures. So there's a giraffe texture here, but it doesn't look at all like a giraffe compared to the tracks output. Similarly, for other images containing people or zebras in particular, the tracks output is generally better than attention GAN outputs. We also conduct quantitative and qualitative results by humans. So on FID and IS, on the COCO split of localized narratives, we observe that tracks outperforms attention GAN. But when you transfer the models to open images, attention GAN performs slightly better. And we think that this is because we make a lot of use of MS COCO semantic segmentation classes and objects. So it has a bit more of a generalization problem compared to attention GAN, which is trained just on the descriptions. But when you evaluate attention GAN and tracks, when you present attention GAN and tracks to humans for evaluation, they usually rate tracks much higher for image realism. So on localized narratives, the COCO split, tracks is preferred 77% of the time, and on open images, it's also preferred around 77.2% of the time. When you ask human evaluators to evaluate how well aligned the generated image is with the caption, tracks is also significantly higher than attention GAN. So on COCO, it's 52%, and on open images, it's 46%. So I think while we managed to synthesize images from mouse traces and descriptions, and I think we're the first to consider this combination, this tracks model has some inherent problems. So I think the most glaring one is that it's a multi-stage model, which is easy to train because you can train each stage in sequence. It's also very interpretable because for each stage you can get the outputs and you can look at what they do at each stage. So it's very easy to debug. But the problem is that this kind of multi-stage model is very troublesome because you have to train essentially 4 models in sequence compared to an end-to-end model that you just train once. The other problem is that the vision and language grounding in this model is very implicit. And the main place that it comes from is from our noisily annotated data, where we use mouse traces and segmentation masks to assign class labels to each word. So there isn't very explicit grounding in this case. And we think that models with stronger grounding would likely perform better. So the question comes up with, the question that comes up is whether we can train models with explicit multimodal fusion supervision end-to-end and achieve stronger results. And this was what led us to our other work titled Cross-Modal Contrastive Learning for Text-to-Image Generation, which was presented at CVPR earlier this year. So the idea for cross-modal contrastive learning was inspired by recent advances in image pre-training. So I think there was some recent work in image pre-training which showed that contrastive learning was very effective for learning good representations. So contrastive learning essentially is trying to learn embeddings that are close together when the images are similar and far apart when the images are different. And this is normally done by in practice by minimizing some cross-entropy-like loss. And we find that this is roughly equivalent to maximizing a lower bound of the mutual information. So we apply these contrastive learning losses in XMC GAN for text-to-image synthesis. So the idea is fairly simple. With a particular caption, we want to synthesize an image from it. And we want this image to be close together in embedding space to the corresponding real image. We also want this generated image to be close together in embedding space to the synthesized caption. So this is the arrow here on the right. And lastly, we also want, of course, the real image to be close together in embedding space to the text encoder. So you can't make up like some arbitrary embedding space for just your generated images. We also want images to not be close together in embedding space, but we also want them to be far apart in embedding space from things that are different from them. So for example, this second image that talks about a boat, we want it to be far apart in embedding space compared to the baseball player image. So at the end, you have this encoder that is able to map images in some low-level embedding space that describes their content. So in our application, we implement 3 different contrastive pairs. So the first is the global sentence embedding with the global image feature. So the global sentence embedding is a single vector that describes the content of an entire sentence. So you can think of it as a summary or the class token in BERT, which summarizes the entire description. And this global image feature is similarly a feature that describes the overall content of an image. And it's normally done by pooling together the outputs of some pre-trained network. We also apply contrastive learning between the word embeddings. So these are a sequence of word embeddings for a sentence. If your sentence has T tokens, then you have T by 768 tensor describing the word embeddings. We contrast this against image region features. So in our case, we look at each 16 by 16 patch of the image, and we see whether that patch is aligned to certain words in the description, for example. So it's important that for these cross-modal pairs, for these text image pairs, we train the discriminator with just the real pairs and train the generator with just the fake pairs. So this is actually quite important. That we found that this was quite important. Otherwise, there's a huge imbalance in the discriminator and generator. And lastly, we also apply a more standard image-image contrastive loss between the real images and the generated images. So this is quite similar to some reconstruction or perceptual loss. So this is how the cross-modal pair is implemented.
JY, so for the fine-grained contraction loss, then I think the data is quite limited. How do you get this kind of fine-grained kind of grounding data, let me see in this way, for the second loss?
Yeah. For the second loss, yeah, that's a good question. So I think the problem is that we don't have, for each caption, we don't know which patch each word refers to. So like in this caption, we don't know which patch the baseball player refers to. So how we solve this in our case is we actually just we learn 2D attention to attend to each word. So each image region will attend to each word, and it essentially learns which word it should attend to. And for each word, it also attends to every image feature. So it also tries to learn which image features are important. So this is like very noisily annotated data. It's not annotated actually. It's very noisy data, and I think like similar methods were also used in attention GAN and other attention-based generation models.
Okay, so this fine-grained one, in fact, is still a global contraction loss, but with the attention mechanism kind of inside, so that we hope that the attention mechanism will do the fine-grained correspondence.
Yeah, that is exactly right.
Okay, got it.
Yeah.
So the image region here is the grid, kind of the grid region. It's not, for example, some object detected region.
Yeah, that's right. I guess this is a bit unclear. So this R is actually, this tensor should actually be 16 by 16 by 768, for example.
Okay, got it. Okay.
Yeah, thanks for the question. Yeah, so these contrastive losses are normally implemented as follows. You have some image encoder that encodes your image xi. You have some sentence encoder that encodes the corresponding sentence si, and you try and maximize cosine similarity between them. And conversely, you have some sentence embedding for a different sentence sj, and you try and minimize the cosine similarity between your image I and the different sentence sj. So the XMC GAN architecture, I won't go too much into detail about it, but I like to mention that it's a very simple model, and we didn't make many architectural changes to the XMC GAN model. So it's a very simple one-stage model compared to prior work, which sometimes use two-stage approaches for generating images. So some prior work, they try to synthesize an image at 64 by 64, followed by 128 by 128. and finally 256 by 256. But for XMC GAN, we synthesize the final 256 pixel image directly. This is more efficient, and also we find that having the contrastive losses makes this training much more stable. So we don't even need multi-stage approaches to be able to synthesize good images. Yeah, so as I mentioned, the contrastive losses are in these yellow circles here, and we implement them in the discriminator. So the discriminator acts as a feature extractor for the contrastive learning features. So we essentially just add additional fully connected layers that output features for the contrastive learning. So we don't need an extra feature extractor for the contrastive losses. The discriminator is trained jointly with the adversarial loss and the contrastive losses. As for evaluation, we evaluate it similarly on 3 datasets: the MS COCO dataset, the localized narratives dataset, which contains the MS COCO split and the open images split. So as I mentioned before, localized narratives contains much longer descriptions, so 42 words on average compared to MS COCO, which is 10 on average. The open images data is also slightly longer, and it's important to note that open images actually has generally very complex scenes, so around 8 objects per image on average. So here are some qualitative results comparing against previous methods. So on the left here, you can see the MS COCO results. And these are 3 state-of-the-art models, and XMC GAN is on the right here. So XMC GAN, I'm biased, but XMC GAN overwhelmingly outperforms prior work when it comes to qualitative results. So if you look at the caption that says a green train is coming down the tracks, a lot of these prior state-of-the-art models, so OP GAN was the state-of-the-art before XMC GAN, they couldn't generate any objects that really look like trains, but XMC GAN is capable of synthesizing a very realistic and whole-looking train. Similarly, for captions about skiers, and also this caption about a kitchen is also much better for XMC GAN compared to prior work. For localized narratives, we also compare to attention GAN and the tracks model that I described before. And even though XMC GAN doesn't use the mouse traces, it's still able to synthesize much better images compared to tracks or attention GAN. So you can see that the image about skiing here is much better than prior work. The image about the train here is also much better than the other 2 models. So XMC GAN is able to synthesize trains and also animals very well, I guess because they occur very frequently in MS COCO. When you ask human evaluators to rank different models, XMC GAN is also much preferred over the other 3 state-of-the-art models. So about 77% of the time, XMC GAN is rated as best for image realism, and about 74% of the time is rated as best for language alignment with the caption. In terms of quantitative scores, and FID is the most important metric here, XMC GAN outperforms prior work by a very significant margin. So the next best model is OP GAN, which achieves FID of 24.7, while XMC GAN improves FID by a percentage point of 62% to 9.3 FID. So we're getting very close to the FID of the real images. I'd also like to discuss some ablation experiments we ran on XMC GAN. And I think the most important thing to show here is that the baseline XMC GAN model, which I claim was very simple, achieves quite poor results on FID. So the first row here is the model without any contrastive learning. And you can see that FID score is around 39. So this is much worse than previous state-of-the-art, which had FID of 24. But when you add the contrastive losses, so if you just add the global sentence and global image contrastive loss, this improves FID by about 20 points to 19, which is already better than the previous state-of-the-art. If you add just the word region, which is the fine-grain contrastive loss, FID is also improved to 24, but it's not as good as the global sentence loss. However, if you add both the word and the sentence loss as shown here, the FID improves to about 14.25, which is the largest increase out of any 2 losses. And finally, if you add the image losses coming from either VGG or the discriminator hit, this further improves FID slightly to 11 points. So this is like where we get our best model. And I should mention that these scores are slightly different from the ones before because they're computed using a slightly different TensorFlow model for the ablation experiments. But the ones presented before, the
Yeah,
So,
JY, we cannot hear you.
Oh, sorry.
Oh, now we can hear you now. Yeah.
Oh, okay. Do you miss a lot of what I said? I hope I wasn't talking to myself.
No, just a few seconds. It's fine.
Okay.
Yeah.
Okay, yeah, that's good. So I'd like to share a bit about the image diversity of XMC GAN. So in MS Coco, you have 5 captions for each.
JY, in fact, can you go back? Oh, just now you didn't mention much about the image noises.
Oh, yeah.
What kind of image noises you are using here?
Right. I think maybe that part might have been cut out. So for the image loss, we tried 2 different losses. The first is we use a VGG model that was pre-trained on ImageNet. So I think this VGG model is quite standard when people try to implement perceptual losses in generative models. So we use a VGG model to compute image embeddings between generated images and real images. We found that the VGG itself wasn't very helpful. We add another head to the discriminator, which computes image features for real images and generated images. So this was more useful than the VGG losses. And we think this is because by adding the discriminator head, you force the discriminator to be trained to do contrastive learning on images. So these are like the 2 image losses that we use. Out of these 2, the discriminator loss seems to be more important by itself. But when you add all the losses together, the model that performs the best seems to be using VGG and the sentence and the fine-grained word region loss. Okay.
In fact, I do not quite understand why kind of this model has such a huge improvement compared with previous model. Because this model is still one stage, and for example, for the contrast loss, this kind of thing. For example, as you mentioned, even the local contrast loss and also the global contrast loss has been used in attention GAN already, but it's not used as discriminator. It's just as actual loss. That's kind of retrieval model is pre-trained and then just use an actual loss as, for example, a reward to train the model. So seems that all the components are somewhere there already, but why we have such a huge kind of performance boost?
Yeah, I think that's a good question, and we were also very surprised that it was so effective, even though the idea itself is very simple. And I think the main reason, or like one of the main reasons, is that unlike previous work, we apply the contrastive losses mainly on the discriminator. So the discriminator provides the feature embeddings for all the contrastive losses. And this forces the discriminator to be trained to be very strong, such that it can discriminate between different images. So I think that's the reason that we believe why this model performs so much better, because we apply it on the discriminator rather than just the generator.
So then how many heads this discriminator have? Has. So I guess that this discriminator will have for example, say a backbone, but it should have many different heads. One head is trying to do the kind of previous GAN style stuff to get the logic to discriminate whether it's true or false, but should also have some other heads for contrast loss, have some other heads for perception loss. So how many heads do we have for this discriminator?
Yeah, that's a good question. I think actually the discriminator only has 3 heads. So, sorry, the discriminator has... Yes, the discriminator has 3 heads. So the first one is the real fake prediction adversarial loss, as shown on the bottom here. The second one is a is a head here for creating the global image feature. So this is like some pooling operation that creates a vector for each image. It has a third head for computing the region features. So this is just a 1-by-1 convolution that takes like a 16-by-16 tensor and converts it to like a 16-by-16-by-768 feature. So we don't do any fully connected layers on the text embeddings, which come from BERT. So we have 3 heads, and the 3 heads are cast to the same dimension as BERT, and we use those to do the contrastive learning.
Yeah, previously, the reason why we do not use kind of share the backbone for the GAN, kind of for the discriminator and the contrast loss is because they are essentially doing different things. The discriminators kind of real fake head is trying to tell the generator that, okay, the ground truth image and the generated image, although they are from the same caption, they should be different. One should be real, one should be fake. So the kind of this head is trying to push kind of the generated one and the real one far away from each other. But the other two noises, contrast noise, if they are from the same caption, that two noises are trying to kind of pull the generative image and the real image together because they are from the same kind of caption. So we think that they should be close to each other, like the picture you have shown. So they are essentially doing different things. So did you observe any kind of conflicting between these three heads during training?
So I think in general, not really. So we did do like some hyperparameter sweeps to make sure that the losses are balanced. But in the end, we kind of found that like having just a weight of 1 for every loss was sufficient. So yeah, I agree. It's kind of weird that the adversarial loss and the contrastive losses play nice with each other. But it could also be, I guess, like the discriminator. Like it could also be due to like more modern training tricks, I guess, like the spectral normalization and things like that, that allow the discriminator to act as more than one thing.
Yeah, thanks.
Yeah, thanks for the question. Yeah, I think it was also quite surprising to us that it worked so well at first. Okay, so thanks for the question. In the interest of time, I will try to speed up a bit. So I think the question that came up after we trained XMC GAN was that XMC GAN generated images are quite good. They seem to be getting us to that stage where you can use text to image generation for useful things by now. But there are a lot of things lacking from XMC GAN. So there's a question of whether XMC GAN knows how to count. And the answer is no. So if you tell it like 4 men ride horses over a body of water, you can see that it doesn't really generate 4 horses. It's probably more like 5. If you change this caption to 3 men, it also doesn't generate 3. It might in fact like generate more than 5. So XMC GAN doesn't know numeracy. It doesn't know how to count. XMC GAN also doesn't seem to understand what certain words mean. So does it really know what a quarter is in the context of a sandwich? And if you provide a similar caption describing a quarter in the context of money, does it know what that means? And I think the answer is probably no in most cases. So the other question is like whether these kind of attributes like numeracy or compositionality or arrangement of things. So if you tell XMC GAN to generate like a green cube on top of a red cube, it can't really get that correct. Sometimes it generates them next to each other. Sometimes it gets the color wrong. So the question is like whether these kind of features, can we get away with training very large models on curated data? And the recent DALI paper from OpenAI seems to suggest that even if we can't get all the way there, we seem to be able to get a very good amount of the way there. So I guess this is an open question, and I'll say like maybe for now. So these questions also led us to wanting to ground models more closely in the real world. So this led us to our recent preprint released in May, titled Pathdreamer, a world model for indoor navigation. So this is a spatially grounded generative model. And the idea was inspired by how humans navigate in houses. So if you throw me in a house that I've never seen before, and you tell me to go forward, turn right into the kitchen, I have a very good idea of what I'll see in the kitchen, even though I've never been in that house. I will probably see a fridge, a sink, and a table. And this is because I know that houses have certain structure, and kitchens look a certain way, and bathrooms look a certain way. So the question is, can we train computational agents to do the same thing? Can we provide them with one single input image and allow them to synthesize the remainder of the house as a 3D environment? This line of work is roughly known as world modeling, and a lot of prior work use this in game-like environments. So over here you can see David Ha and Jürgen Schmidhuber tried this for the first time in 2018, where they applied world models in the context of OpenAI racing, the gym environment, and also the Doom game. Others have also applied this to Atari games, where they synthesize predictions in future time steps in very small pixelated 2D space. So in contrast, Pathdreamer aims to synthesize high-resolution 360-degree images in using just a single input image. So Pathdreamer synthesizes the depth, RGB, and segmentation outputs for any amount of steps away, given a single input image. So given the image at the start, Pathdreamer is able to synthesize the remainder of the house up to a certain distance. And what is interesting in this example is actually, if you notice at the start of the video, it sees only just the corner of a kitchen, but it's able to infill most of the kitchen quite accurately. So all of this would be very useful for sampling-based planning or data augmentation. If we can synthesize 3D environments from just a single observation, then that gives us a lot of data to work with when we train embodied agents. Pathdreamer is a relatively simple model. So it consists of two stages. In stage 1, the structure generator, we take previously seen segmentation and depth outputs, and we store them as a 3D point cloud. When we want to predict new images for different locations, we project this 3D point cloud into 2D guidance images. So given a new location, big T, subscript small t, we can retrieve the guidance images for segmentation and depth outputs. These go into an encoder, which is essentially just a ResNet50. And this is decoded, which is the mirror image of the ResNet50, into a high-resolution segmentation and depth image. So these are the predicted segmentation and depth for the new locations. We also impose this stochasticity in the model. So this module on the top is essentially learning a prior distribution for the data. It learns some Gaussian with a learned mu and sigma variable, and this allows us to sample different random noise for stochastic generation. And I'll go a bit more detail into this later on, why we think is important. Provided with the generated segmentation and depth outputs and previously seen RGB images, the stage 2 image generator is a modified spate model that takes these outputs and synthesizes a realistic RGB at the new location. So this uses the generated segmentation and depth. It takes the guidance RGB from previously seen images, and it synthesizes a real image. So this stage 2 model is trained using adversarial loss and some reconstruction losses. So given one input image or multiple input images, for example, here we see an input of a depth, a segmentation, and an RGB. Pathdreamer is able to synthesize outputs up to 6 or 7 meters away at quite good resolution. So Pathdreamer synthesizes, these are Pathdreamer outputs at 1 step away. In this case, it's around 0.9 meters. So you can see the depth, the segmentation, and the RGB are all quite good. And in this case, the RGB is quite well aligned to the ground truth, shown on the bottom row. If you query it for a different step away, so at this point it's around 2.2 meters, it synthesizes a fairly decent looking image, although we can see here that there are some blurry regions and some glitchy regions, and it's a bit more different from the ground truth image in this case. And same for 4.2 meters away, 3 steps away, and 4 steps away. So the image quality generally gets worse, but we observe that even at 5 meters away, the generated image is quite realistic and quite plausible. So in the context of data augmentation and downstream tasks, we don't necessarily want predictions to match the ground truth exactly, but we just want the predictions to be realistic and plausible, such that we can use them for other things. So there's an interesting failure mode here where you see that the ceiling rafters being generated here actually end abruptly. So as humans, we kind of know that these kind of beams on the ceilings, they usually go all the way because they are either support structures or some decorative element. But Pathdreamer has not learned to do this, probably because it's not well represented in the segmentation or depth or RGB space. So I think that's an interesting failure mode. As I mentioned earlier, we also want Pathdreamer to be diverse and stochastic. So given one input image, it's not possible to deterministically generate one output image all the time. So for example, if you tell me to go into a room I've never seen, I might know that it's a bedroom, but I don't know what will be in that bedroom. I can provide several informed guesses. So in this case, Pathdreamer can do something similar. For the unseen regions, by sampling different noise vectors from the learned prior, Pathdreamer can synthesize slightly different things. So in this case, sampling one noise vector gets us a chair, a window, and a table, which is also well represented in the RGB image. Sampling a different noise vector gets us a cushion, a chair, and a bed instead. And in this case, noise vector Z2 gives us the prediction that is closely matched with the ground truth. And you can see on the left here, Pathdreamer actually synthesizes a painting on the wall on the left, in this case. If you sample yet another noise vector, the painting becomes a door and it synthesizes a table instead. So all of these predictions, while they look very different, and one of them in particular is well matched to ground truth, all of them are plausible predictions that Pathdreamer has synthesized. So all of these are useful predictions. In the event that you just want one prediction, you can probably achieve that using some re-ranking model as a post-processing step or something. So one of the reasons we developed Pathdreamer is to apply it to embodied AI tasks. So we tried it here in the context of vision and language navigation. So the vision and language navigation task is that you're given a natural language description, such as move forward, turn left into the bathroom, and stop by the sink. And your agent has to navigate in a 3D environment to execute that task. So the baseline model, shown in green, has a success rate of about 37% when you roll out for one step. And if you cheat by using the ground truth data for planning, you can see that this improves to slightly above 40. So in our experiments, we replaced the ground truth images with Pathdreamer generated images. So this is completely fair since Pathdreamer doesn't use any information that the agent hasn't already seen. And we find that Pathdreamer is able to close about half the gap between the baseline model that doesn't use planning and the model that cheats by using ground truth images from planning. So we think this is quite promising, and we look forward to Pathdreamer being used for more embodied AI tasks other than VLN. So this brings up another question of how important structure is, which I think I also mentioned in the image generation work. A lot of these inductive biases that we have introduced are useful in the context of the task. So for example, I mentioned that we use guidance image inputs for Pathdreamer, and these are synthesized from some 3D point cloud that are projected into 2D space. And this inductive bias makes a lot of sense to us, since if you go to a new location, you remember all the things that you have seen before, and you generally just don't know about the black regions in this case that you have never seen. But this also leads to some artifacts when you treat it like a 2D image. For example, on the left here, you can see that the door class, which is in blue, has somewhat leaked, and the model can see it as a 2D image, even though there's supposed to be a wall in front of it in the ground truth image. And similarly for the bed here, it's supposed to be obstructed by a wall, but because of the way we do 2D projection, it's visible to the model. So there's an interesting question of whether things like that are harmful to Pathdreamer or the overall pipeline is actually still useful. And I think this fits into the broader question of whether we should continue training large models with small inductive biases like transformers on large data, or if we should continue training more specialized models. And I don't know the answer. So to conclude, today I've presented 3 of our efforts into grounded visual generation. The first is we use mouse tracers as a proxy for user attention to create image generation results that are aligned with both language and user attention. We also enforce vision language grounding more explicitly, which allowed us to achieve state-of-the-art on MS COCO image generation. And lastly, I presented a preprint that we released recently about spatially and geometrically grounded generation. So I think generative models are interesting to me because they learn from real-world data and they encode meaningful and interesting structure about the world. So text-to-image generation models learn the ambiguities of language and they learn how to represent this in images. Models like Pathdreamer also learn 3D geometry of the world. And I hope that future models will also learn concepts about physics. So one interesting question is that if you tell an image generation model to do something like generate an image of an anvil in a hammock, does it know that the anvil is much heavier than the hammock? And does it know that the hammock will have creases when you generate this image? So these kind of concepts of physics, are they learnable by generative models? And if so, will simply increasing the size of the model get us there, or will we need to do something different? And to conclude, I think generative models are amazing ways to represent the knowledge of a data set or of a model, because they're so easily interpretable. And I believe that grounding these in language, audio, geometry, or even physics will improve them further and allow us very creative ways to control the outputs. And of course, thanks a lot for my amazing collaborators. And thanks a lot for inviting me to share here. I think we have maybe 1 minute or so left, and I'll be happy to take any questions if there are any.
Yes, thanks, JY. So any questions for JY? So before people are composing their questions, I have a question about the grounding part. You talk about 3 kind of works here. In fact, I only see that only the first one is really using kind of grounding annotations to you really have kind of data about grounding to inject grounding information into the model. For the later 2, especially for the second one, it's really the data do not have grounding at all. It's just we implicitly learn some grounding for that. In fact, I got surprised in the second work. Why don't you just use the local narratives to design some laws for the for the second work? For example, when you do fine-grained contraction laws, how about just use the the local narrative annotation to design the fine-grained laws, so you exactly know which part should be corresponding to which part, instead of need to just learn it blindly from the model.
Yeah. I think actually that idea was something that we wanted to try. I guess like the reason we didn't do it was because it was quite complicated, and at that point, I think because of the encouraging results, we were more interested in like pushing the state of the art for COCO, which is why we didn't focus too much on localized narratives. But I completely agree with you that localized narratives has very interesting grounding, and that should be how we train the models. I guess the only drawback is that localized narratives has significantly less data than COCO. So localized narratives has 1 description for each image. So you end up with around 120,000 caption image pairs for COCO, and a bit more for open images. But for MS COCO, you have 5 captions for each image. So that gives you a lot more training data on just the COCO side.
Yeah, thanks. So is there any other questions? So if there's no more questions, let's end the talk here. Let's thank the speaker again. Thanks, JY, for visiting us and gave a wonderful talk.
Thank you. It was a very fun visiting Microsoft.
Yeah. Thank you. So I think we have several follow-up one-to-one discussions with JY. So hope that JY enjoy the follow-up discussions.
Yeah, definitely. Thanks so much for organizing this.
Okay, thanks. Bye-bye.
Okay, bye.